Every time you write a SQL join, something interesting happens behind the scenes. Your database doesn't just magically combine two tables, it has to make a choice. It picks from a handful of algorithms, each with completely different performance characteristics. And the wrong choice? It can turn a 50-millisecond query into a 50-second nightmare. That's 1,000 times slower. Same data, same tables, same result. The only difference is the algorithm used to combine those rows. Most developers never think about this. They write join, get their results, and move on. But understanding what happens underneath gives you a massive advantage when queries start slowing down. In this video, we'll crack open the join keyword and explore the three major algorithms that databases use to combine your data: nested loop joins, hash joins, and sort-merge joins. Let's start with the basics. Before we dive into algorithms, let's make sure we understand the problem. Here are two tables: employees with an ID, a name, and a department ID, and departments with an ID and a department name. The employee table has a foreign key department ID that references the department's table. When you write a join query, you're asking the database to match each employee with their department. Alice has department ID 1, which maps to engineering. Bob has department ID 2, that's marketing. Charlie is also in engineering. The database needs to find every matching pair and combine them into a single result row. That's the core problem. Given two tables and a join condition, find all the matching pairs. Sounds simple enough. But when these tables have millions of rows, the way you search for those matches makes all the difference. Let's look at the simplest approach first. The most straightforward way to join two tables is the nested loop join. The idea is dead simple. Take the first row from the outer table and compare it against every single row in the inner table. If the join condition matches, output that pair. Then move to the second row of the outer table and scan the entire inner table again. Repeat for every row. Let's watch it work. Alice has department ID 1, we scan departments. ID 1, engineering. Match. ID 2, marketing. No match, ID 3. Sales, no match. That's 3 comparisons for one row. Now Bob, department ID 2. Scan again. 1, no, 2, match, marketing. 3, no, another 3 comparisons. With 5 employees and 3 departments, we do 15 comparisons total. The complexity is O of n times m for small tables. This is perfectly fine. But if both tables have 1,000,000 rows, that's 1,000,000,000,000 comparisons. We need something smarter. What if instead of scanning the entire inner table every time, we could jump directly to the matching row? That's exactly what an index gives us. If the department's table has a B-tree index on its ID column, we don't need to check every row. We traverse the tree. Start at the root, go left or right based on comparisons, and land on the exact row we need in just 2 or 3 steps. Watch the difference. Alice has department ID 1. Instead of scanning all 3 departments, we traverse the B-tree. Root, left child, leaf. Found engineering in just 2 comparisons instead of 3. Bob, department ID 2. Root, right child, leaf. Found marketing. 2 comparisons again. The complexity drops from O of n times m to O of n times log m. That log m is huge. If the inner table has 1,000,000 rows, log m is only about 20. Instead of 1,000,000,000,000 comparisons, we're down to 20 million. That's why indexing your foreign keys is one of the most important things you can do for query performance. But what if there's no index at all? This happens more often than you'd think, especially with temporary tables, subqueries, or analytical queries. This is where hash joins shine. A hash join works in 2 phases: build, then probe. In the build phase, we take the smaller table and load it into a hash table in memory. Here's how it works. Take each row from the department's table. Apply a hash function to the join key. Department ID 1 hashes to bucket 0. Department ID 2 hashes to bucket 1. Department ID 3 hashes to bucket 2. Now we have a hash table sitting in memory with all the department rows organized by their hash join key. Each bucket contains the rows that hash to that position. The key insight is that we always build the hash table from the smaller table. This minimizes memory usage. If departments has 3 rows, the hash table is tiny. Even if employees has millions of rows, the hash table stays small. Now we're ready for the probe phase. Now comes the elegant part. We scan the larger table, the employees, 1 row at a time. For each row, we hash the join key and jump directly to the matching bucket. Alice has department ID 1, hash it, bucket 0. Look inside, there's engineering. Match found. No scanning, no searching, just one direct lookup. Bob has department id 2, hash it. Bucket 1, marketing is right there. Another instant match. Charlie, department id 1 again, hash it. Bucket 0, engineering, match. Notice what just happened. We scan the departments table once to build the hash table. Then we scan the employees table once to probe it. 2 passes through the data, that's it. The total complexity is O of n plus m. Compare that to the nested loops O of n times m for 2 tables with 1,000,000 rows each. That's 2 million operations instead of 1 trillion. Hash joins are incredibly efficient when you have enough memory to hold the smaller table's hash table. There's one more major algorithm. The sort merge join. It works like a zipper. First, sort both tables by the join key. If they're not already sorted, the database sorts them. Employees sorted by department, id department sorted by id now. Place a pointer at the start of each sorted list. Compare the keys. If they match, output the pair and advance. If the left pointer is smaller, advance it. If the right pointer is smaller, advance that one instead. Watch it work. Left pointer department id 1, right pointer department id 1, match, output Alice and engineering, advance left. Charlie also has department id 1, match again, advance left. Now left pointer has department id 2, right pointer still on 1, right is smaller so advance it, right pointer now on 2, match, Bob and marketing. The sorting step costs O of n log n plus m log m, but the merge itself is just O of n plus m, and here's the best part. If the data is already sorted, maybe because of a clustered index, the sort step is free. Sort merge joins love pre-sorted data. So how does your database choose between these algorithms? It doesn't guess. It calculates. Every database has a query optimizer that examines your query and your data before execution. It looks at table statistics. How many rows does each table have? Are there indexes available? Is the data already sorted? How much working memory can it use? For a small inner table with an index, the optimizer picks an index nested loop join. The index lookups are fast and memory usage is minimal. For 2 large tables with no useful indexes but plenty of available memory, it chooses a hash join. Building a hash table in memory is worth the upfront cost when it eliminates billions of comparisons. For pre-sorted data or range-based join conditions like greater than or between, sort merge join wins. The merge phase handles ranges naturally, and if the sort is already done, it's practically free. The optimizer estimates the cost of each strategy and picks the cheapest one. This all happens automatically every single time you run a query. Let's put all 3 algorithms head-to-head with real scenarios. Scenario 1, a small lookup table with an index, 10,000 employees joining against 50 departments. The index nested loop join dominates here. Each of the 10,000 lookups takes microseconds through the B tree. Hash join and sort merge are overkill for a table this small. Scenario 2, 2 large tables, no indexes, plenty of memory. 1,000,000 orders joining against 1,000,000 customers. Hash join wins by a landslide. It builds a hash table from customers, then probes with orders. Linear time, minimal comparisons. Scenario 3, pre-sorted data with range conditions. Joining time series events against time windows using a between clause. Sort merge join is the clear winner. The data is already sorted by timestamp, so the sort phase is free and merge handles ranges beautifully. There's no single best algorithm. The winner depends entirely on your data, your indexes, and your query. That's exactly why the query optimizer exists. Let's bring it all together. Every SQL join triggers an algorithm choice. Nested loop join, the simplest approach, checks every possible pair. Great for tiny tables, terrible for large ones. Index nested loop join uses B-tree indexes to skip the full inner scan. This is why you should index your foreign keys. Hash join builds a hash table from the smaller table and probes it with the larger one. Linear time, incredibly fast for large unindexed joins. Sort merge join sorts both tables then merges them like a zipper. Perfect when data is already sorted or when you're doing range joins. And the query optimizer automatically picks the best one for every query you write. Want to see which algorithm your database chose? Run explain analyze before your query. It shows you the exact execution plan, including which join strategy was selected. Next time you write a join and it's slow, you'll know exactly where to look. Thanks for watching.